Hello everybody. I want to go over a Newton's method problem with you from the start. I want to go through it very quickly, just theoretically, like the other video did, but then I also want to go through the calculations with you. They are not difficult, they are tedious. More than anything, I want to show you, give you some hints as far as how to organize your information. So as you're moving through this, you're not getting kind of lost with your numbers, and we need to talk about making sure to keep your accuracy by using your calculator. So you're going to want your calculator in front of you, your grapher, because we want the capability to store numbers in your calculator. So you want to have that in front of you, and you probably want to have some scratch paper in front of you if you don't already, which of course you do. All right, I thought you could see my face, but I'm not sure you can, so I guess it doesn't matter. All right, so Newton's method, we said, uses linearization over and over and over again to approximate the zero of a function. Now we're just going to look at a quadratic here for the sake of simplicity, but you can see here this quadratic has a zero somewhere around 3. It looks like it's a little more than 3. And then of course I made a terrible guess of 10 because I'm a terrible guesser, and I drew a tangent line at 10. And you can see here that if you follow that tangent line down to its 0, it's still terrible. It's almost 7, but it's closer than 10. So my first guess of this 0 is 10. If I write an equation for the tangent line at 10 and I find its 0 instead of trying to find the function 0, I get a first approximation, we call it, of just shy of 7. All right, now obviously that's not good. So what we do is we say, okay, I'm going to take this first approximation and I'm going to do that process all over again. So whatever this value is, it's just shy of 7, I'm going to take that and I'm going to jump back up on the curve at that value. So notice here, this is where my first tangent line, my red tangent line, crossed the x-axis. I'm going to jump on the curve at that same point. So again, look, I went from just shy of 7 is the 0 of my first tangent line. That becomes, my goodness, the location of my new tangent line. So that's one of the most important things to know about Newton's method, that the 0 of your tangent line is what's going to produce your next number for your approximation. So we would call this number that's just shy of 7, our first approximation. And now this green line is going to give us our second approximation. Notice if I wrote the equation for this green line and I find its 0, it puts me even closer to where I want to be. So my red line's way out here. I do a second approximation, follow that line. Now I'm right around 5. And what we're going to do is we're just going to keep doing this over and over and over again. We call them iterations. And here's the thing. The numbers can get messy, right? You start getting these nasty fractional values, but that's okay because when we're going to store them in our calculator. And it is not lost on me that we are using our calculator to manipulate all these disgusting numbers and storing it when we could just use our calculator to hit second calc 0. I realize it's annoying, but the thing is, probably what's going to happen, if you're taking an in-person AP, your Newton's method question will be no calculator, because you won't be surprised to know that there's a program for this as well. If you're taking the AP online, or if there is a Newton's method question on a no calculator or on a calculator section, it'll be a more theoretical question where you have to understand the concept of Newton's method and what it does versus manipulating numbers. All right, so we're going to take this second approximation and we're going to turn it into a third approximation. So notice here, I took my green line, jumped back up to the curve, new tangent line, and I zoomed in on it over here. When you get the 0, your green line, right back up to the curve, make a new tangent line. Use this x value to make a new tangent line. It brings you even closer. Every tangent line that we do brings us a little closer. So if I use the 0 of this, which looks to be slightly more than 4, jump back up on the curve, that'll give me my fourth approximation. So again, look, here's my purple tangent line. It crosses right here. I jump back up on the curve. I draw a new tangent line, and it brings me even closer. Every time I draw a new tangent line, it brings me even closer. Here's a fifth approximation. As you can see, I had nothing better to do with my time. So here's my fourth approximation. Here's my fourth tangent line. Follow it up to the curve, draw a new tangent line, swoop. We're getting really close here. I mean, look at this. This is only between 3 and 4, and I'm really, really close to my tangent line here. So just for fun, I put all of them in one picture, and I don't know how useful this is, but what you can see here is the slopes of your tangent lines are getting less and less and less steep. They're honestly, what they're doing is approaching the slope of the tangent line at that 0, which we know at that 0, that's the bottom of the parabola, is going to be exactly 0. Right? The slope of that tangent line at the bottom of this parabola is going to be 0. So what we see as we do these approximations is our tangent lines approaching the tangent line that we're actually after. Now, we'll never actually get there, but we can approach it. And that's what calculus is all about, right? Doing things an infinite number of times and never really getting there. All right. Okay. So this is the actual equation. It was the 0 of it was 3.3. But as you saw, we got really, really, really close to it. All right. So what I want to go over with you today is how to actually go through this process numerically. And also how to know how many times do I have to do this? Like how many approximations do I have to do? How many iterations of this? How many tangent lines do I have to draw or write? Now, the easiest thing that could happen is they could say, do the first 3 approximations or do the first 4 approximations. That's the best thing that could happen. And if that happens, and the only thing you really have to realize is that your guess that we're going to do in the first step doesn't count as an approximation. So if they say to do the first 3 approximations, then you're going to be writing 3 equations for tangent lines and finding the zeros of them 3 times. You don't get to count your guess as, quote, an approximation. It's not. It's just that. It's a guess, right? That's the easiest thing that could happen, is that they just tell you flat out how many approximations you want to do. But of course, they might not. And so I figured we'll go with the more complicated situation here. And I shouldn't even say it's more complicated. You just have to pay a little closer attention to what you're doing. So what they tell us here is how accurate they want us to be. And I think this is probably a more realistic situation. If you're actually a person who's working in the world and you're using this method, a really important question would be, how accurate am I? Right? If I need to be accurate to 5 decimal places, I need to know that I'm accurate to 5 decimal places. So we're going to go through an example where you can tell how accurate you are. I'll show you how we do that. It's pretty simple. So we want to be accurate to 7 decimal places. So again, we're going to start off the same way we always started off, and we're going to start out with a guess. I'm going to make a bad guess, but it's not going to be too horrifying. My guess is 0. All right, so I'm going to say, I see the 0 of this function here. It's clearly negative, but I'm going to start with a nice simple number. I'm going to start with 0. Okay, so that's my first guess. And that's the first thing that you always have to do. Now, there is almost no chance that you're not given what your first guess should be, because if they don't give you what your first guess should be, everybody's going to have different numbers. And that is a logistical nightmare. Trust me, I know. I gave a test once where I didn't tell them what their first guess should be. God help me. Okay. They're probably, if they're smart, going to tell you what your first guess should be. All right, so once we have our first guess, and mine is 0, our job is going to be to write the equation for the tangent line at that point. Now, if you want to draw a picture and draw the tangent lines in, go for it, but you don't have to do that. Okay. Now, in order to write the equation for a tangent line, I need 2 pieces of information. The same 2 pieces of information that I needed in Algebra 2 and Algebra 1 when I was writing equations for lines. I need a point and I need a slope. Now, in calculus, we know where we're going to get our point. Why does it keep doing that? Oh, mercy on me. Okay, we know where we're going to get our point. Our y value is always going to come from our function. Okay. So if I plug in my first guess of 0, I can get a y value out of this. And if I plug in my first guess of 0 into my derivative, I'll get my slope. So these 2 equations are going to stick with me through all of my iterations, because every single time I do an iteration, my y value, I'm going to have an x value. I'll get my y value from the function. I'll get my slope from the derivative of the function. So do yourself a favor, and before you even do anything, get these 2 equations handy, write them down. This is where I'm getting my y value. This is where I'm getting my slope, and keep them handy. You'll want to refer to them. We're going to refer to them over and over and over again. Okay, so in this particular one, this is my first iteration that I'm going to do. I'm calling this x sub 0 because, again, it is not an approximation. It's just a guess, so I don't want to trick myself into thinking it's a guess. So I call it x sub 0, and that is 0. So based on that, my y sub 0, in other words, my first y value that goes with my guess, is a 1. If I plug 0 into this, I just get a y as 1. And my first slope, the slope that I'm going to get, I plug a 0 into here and I get a 3. Okay. So from this we see that we now have a point, 0, 1, which was already on the graph. We kind of knew that. And at that point, the graph has a slope of 3. And that's important to us because those are the two pieces of information we need to write the equation for the tangent line. Now, I have stressed over and over to you that point slope form is the way to go. If ever there is a time to use point slope form, this is it, kids. This is it. All right, so if I use point slope form, it's just going to be y minus my y value equals my slope, x minus my x value. And again, I stress to you, point slope form, these numbers are going to get yucky. By the next step, we're going to have fractions. If you want to mess around with y equals mx plus b on this, have at it, but you probably really don't want to. All right, so if I take my equation for my tangent line, this one is pretty easy to simplify out. It turns into y equals 3x plus 1. Again, first iteration, numbers aren't difficult, but as we move through, the numbers will get more difficult and hard to deal with. All right, so here's my first equation for my first tangent line. So if I draw my first tangent line badly, it's going to land somewhere in here. Again, is that closer to where I want to be as far as the 0? Yes. Is it great? Probably not. It's just a first iteration. All right, so the first thing I need to do, I've got my first equation that I wrote for my tangent line using my guess value. I need to find the 0 of that because the 0 of that tangent line that I just wrote is going to be my first approximation. So again, this is not brain-busting mathematics here. We can find the 0 of that pretty easily. We just set that equation equal to 0, take the 1 over, divide by 3, and we get x is negative 1/3. Okay. Now we'll want to use our brains a little bit, maybe check the graph, make sure we didn't get like a positive number or something. That would be crazy. So I'm at negative 1/3. I'm close to that 0 because that 0 looks like it's somewhere between 0 and negative 1/2. So negative 1/3 probably isn't a bad first approximation. Okay, now what I like to do at this point, now that I have my first approximation, is I like to kind of start a table as a way to organize my information. You're going to get lots of numbers here. It's a really good idea to find a way to organize yourself. So this is what I recommend. Make yourself a table that has these 4 columns. Your x value, your y value, and your slope, because those are the 3 values you need to do an approximation. And then in the last row, what your actual approximation was. So notice here, that should have a repeat on it, and I don't know why it's not showing. My initial x value that I guessed at was 0. The y value and the slope that went with that were 1 and 3. Using those numbers, I wrote the equation for a tangent line, set it equal to 0, and boom, here's my first approximation. So if they say, find the first approximation to the 0 of this function, we're done. That's our answer. Negative 0.3 repeating. Of course, they didn't say that. They said to get it accurate to 7 decimal places. So we're going to keep going. Okay, so at this point, literally, we're just going to start from scratch. We're going to do it all again. The only difference is that now, instead of using 0 as my x value, because that was a guess, I'm going to do it all again using my first approximation. I'm going to do it all again using this x equals negative 1/3. So things that haven't changed is that your y value comes from the function and that your slope is going to come from the derivative. So if I take my negative 1/3 and I plug it into this equation, I get a nice, beautiful negative 1/27. I'm leaving it in fraction form because I have absolutely no desire to write that out in decimal. Okay, my slope, 3x squared plus 3. If I plug this negative 1/3 into that, I get a slope of 10/3. Okay, so if I'm filling in my table at this point, I have x1, y1, and m1. And I'm going to write the equation for a tangent line, and that's going to help me get my next approximation. So notice the approximation I got in the beginning comes right down here, becomes my new x value. I now have a y1 and an m1. I'm going to use it to get my next value, which will be x2, my second approximation. Okay, So in order to do that, I need a tangent line, and I need to find its 0. So let's see. Here's my tangent line, right? Point slope form. Y minus the y value, so since my y value was negative, it's going to become a plus in the equation, equals my slope times the quantity x minus the x value. So again, negative x value turns into a plus here. So I'm going to take this, I'm going to set it equal to 0, and solve it to get my second approximation. All right, so here's my table. Again, I want my second approximation. This is where the math might get a little dicey, and this is where I would recommend storing numbers in your calculator. So the first thing I'm going to do is I'm going to say, okay, well, I know I need the 0 of this equation. So if it pleases you to move this 1 over 27 to the other side and distribute and simplify, you go for it. Because algebraically, nobody cares how you get there. The idea is this: I need the 0 of this equation. So if you want to write this as y equals and then set it equal to 0 and solve it, have at it. For me, I just put the 0 in for y and go from there. Okay. I know I want the 0 of this equation. In other words, I know I want the x value when y is equal to 0, so I just plug the 0 in right then and there. Okay. Then, algebraically, it's our job to solve for x. Now, that can seem a little complicated, and it's up to you, again, the algebraic steps you want to do. I'll show you what I did, and then after I did it, I was like, I probably could have done that a little more simpler way, but oh well. Right. So the first thing I did was I distributed over here on the right hand side. So I said, okay, I'm going to distribute this 10x over 3 and then 10 over 9. Okay. Now I've pretty much got myself well, I want to say a two-step equation, but I said, you know what, I don't want to deal with these fractions. So I multiplied through by 27 just to get rid of my fraction. Do you have to do that? No. You could bring this 10 over 9 over and find a common denominator. Solve it however you want. Okay, so what I did was I multiplied through by 27. So that makes this a 1. My 27 cancels with this 3 to get a 9, so I have a 90x, and my 27 cancels with this 9 to get a 3, so I have a 30. This is a lovely and easy equation to solve, so all I have to do at that point is move my 30 over to the other side. I get negative 29 over 90, and then I get my x value is negative 29 over 90, which you may notice is dangerously close to negative 1/3. Last time it was negative 30 over 90. Now it's negative 29 over 90. And the fact that our slope, or our x value didn't change that much tells us something. It tells us that we're pretty close to where we're going to end up being. If you were really far off, you'd see a big change in your x values. We're not that far off, so we're only seeing a small change in our x value. So I now have my second approximation. So up in my table, my x2 is negative 0.32 repeating. I want you to look at these numbers. This is 0.33333, right? This is 0.3222222. At this point, we are accurate to 1 decimal place. The 3's match. As soon as you get to the second decimal place, they don't match anymore. So after our at our second approximation, we now can tell how accurate we are. We are at 1 decimal place of accuracy, right? Because all we're going to do to figure out our accuracy is compare our approximation to the last one and see how many decimal places match up, for lack of a better term. Okay, so one thing I want you to notice to save yourself a little bit of algebra. Over the years, people always figure this out pretty quickly, and then I'm always like, oh, don't memorize formulas. But it is helpful, and I do use this, but I'm not a memorizer. So in order to avoid all of this algebra yuck and possibly making a mistake, one of the things you can do is you can look at point slope form in its general form and say, okay, well, what's this going to be? The mechanics of it are going to be the same every time. So every time I'm going to write the equation for a tangent line, it's going to be in this form. Every time I'm going to put in a 0 for the y because I want to find the 0 of my tangent line. And so if you look at this algebraically, you can kind of bring it down and simplify the mechanics so that you don't have to go through all this mess every time. Because what happens here is you could easily solve this each time. If you put the 0 in, this just becomes negative y1 over here. Divide both sides by m, then over here you're left with x minus x1. All you then have to do is add your x1 to both sides. So in other words, a really nice shortcut is that you can get your new x value if you take your old y value, or the one you're currently working with, take your y value, divide it by your slope, and then add your x value. So notice my x2 here in the end came from taking my y value, dividing by my slope, and then adding my x value. Now, algebraically, I went through lots of steps to get there, but this is the general kind of gist of it. Now, some people just memorize this, right? I'm not a memorizer, so what I end up doing is every single time taking point slope form and going, okay, this is what I know is going to be true. I'm going to put a 0 in here, and then I solve it out algebraically, and I write this, right? As long as AP understands that this is what you're using, as long as you make it clear to AP that you are using point slope form with a 0 plugged into it, you can just use it, right? So if you write that down one time, then you can go from there and continue to use it. All right, so let's take our negative 0.32 repeating and do another iteration. Okay, we're just going to go and go and go and go and go and go and go until it's as good as we need it to be. And I know what you're thinking. This is a lot of work, and we're only at one decimal place. Two things. It takes a lot longer with me talking about it than it does when you're actually doing it. And you'll be surprised how quickly these decimal places start lining up. So again, I want to make sure, keep these formulas handy. Your y value is always going to come from your slope. Or I'm sorry, your y value is always going to come from your equation, your original equation, your function. Your slope is always going to come from the derivative. Right? So keep those two formulas handy. Right? So notice again, I took my second approximation and I brought it down here because it's now, I'm just going to start from scratch with it. All right, so take a moment, find your y value, find your slope, write the equation for a tangent line, get your third approximation. Okay, let's check it out. Let's see if you were right. When you plug in this value into y, into your function, you should get this really long, nasty decimal. Okay. If you plug this x value into slope, your slope formula, you should get this long, nasty decimal. And from that, you get this long, nasty approximation. Now, let me give you a piece of advice. On your calculator, use the store button. When you get this decimal for x2 up on your screen, right above the on button on your calculator is a button that says store. What I do is as soon as I have this on my calculator, up on my screen, I hit store and I hit alpha A because it's right underneath the alpha key. So I always store my x value in my calculator as A, quote unquote. Right. Then in order to find my y value without any rounding involved, I just type my formula in, but instead of typing the number in, I type A because I've stored A as the number I'm interested in its unrounded form. So what I do is I type a cubed plus 3a plus 1 and I hit enter and my calculator gives me this long nasty decimal. Right? I store that as b. I always store my y value as b. It's just what I do. You do what you want. You could store it as y if you want. Okay. Then I do the same thing. I take my a value and I use it to calculate this slope, right? So I do 3 times a squared plus 3 and hit enter. It gives me this slope decimal. I probably don't have to tell you that I then store slope as c. That's just me. Again, you have the full alphabet on your calculator. So if you want to store these as x, y, and m, go for it. The A and the B and the C are the closest to the alpha button, and I have to move my hand less. And that is literally the exact reason I use A, B, and C. It's sheer laziness. Okay. So then, to find my x value, my next approximation, I can use my shortcut, and I know that I need the negative of my y, so I type negative b, divided by my slope, so I hit divided by c, and then I usually hit enter because I don't trust my order of operations, and then I need to add my x value, so I type, or no, yeah, add my x value, so I hit plus my a value, and guess what? It spits this right out on my screen, and guess what I do? I hit store as a, because that is my new a value. So I keep storing every time I get a new x value, I store it as a. I use it then to find a new y value and a new slope. I store those as b and c. I do my approximation. Okay. So if you make a table like this and you make it known to the AP what formulas you're using to find each one, this is sufficient work to be shown, and I think it's a very nice way to organize your information. Oops, I didn't mean to show you that. Okay, take a moment, see if you can find, oh, before we do that, I'm so sorry, I got a little ahead of myself here. Notice here at my third approximation, look, we're accurate. Remember, this is 3.222222. So look, 3.22. I'm now accurate to 3 decimal places, and I'm really close to being accurate to 4 decimal places. If I rounded, which I'm not allowed to do, I would be accurate to 4. But at this moment, after 3 approximations, we're now accurate to 3 decimal places. So we went from being accurate to 1 to being accurate to 3. Our goal is 7. All right, so let's go again. Take a moment, see if you can find your next approximation. Okay, are you ready? Check these values and see if you got them. You'll notice your y value is extremely small now. Look at this. I got negative 1.31 times 10 to the negative 9th. Now again, there's more decimals to be had here. That's all I wrote down because honestly I don't care. As soon as I get it up on my screen, I'm typing store as B. So I don't need to write them all down. I have it in my calculator stored there. Okay. But your y value is getting small. That's a good thing, right? That's what we want. We're headed toward the 0 of this function. We should be seeing y values that are getting smaller and smaller. We should see y values that are approaching 0. Okay. You'll notice that your slope isn't changing a whole lot. That's also a good sign because that means that you're not making a lot of movement, so that the slope of your tangent lines are starting to look really, really, really similar. Okay. The more you see those two things happening, the more you can be reassured that your approximation is about to be better, right? I should see my y's approaching 0s. I should see my slopes not changing a whole heck of a lot. If you see a really big change in your slope or you see your y value go back up, you probably made a little arithmetic error, so I would check on that. All right. So notice when we chug it out, when we do our negative y over m plus x, look what we get. Negative 0.322185354. 322185335. Boom! Look at that! 1, 2, 3, 4, 5, 6, 7, 8. We are matching out to 8 decimal places. This is what I mean when I said you'll be surprised how quickly it goes. We went from 1 decimal place of accuracy to 3 decimal places of accuracy to boom, 8. So they said they wanted us accurate to 7. We did one better. We went accurate to 8. Okay. So the question is approximate the 0 of this function out to 7 decimal places. Here's our answer right here. I'm actually accurate to more than that, but I don't want to brag. So what we can write is negative 0.3221853 and then stop. Right? Now, that's all they're going to be looking for. If you write the 5-4, fine. Right? But as long as your first 7 are accurate, you'll be in good shape. Okay. Now, again, what this is going to take for you, there's literally almost no calculus here. The only calculus involved is taking the derivative of the original function and recognizing that as your slope. The key to Newton's method is knowing theoretically what you're doing and being able to organize and keep track of your calculations. They are not going to ask you by hand to do more than 2 or 3 iterations, especially if the numbers are getting crazy. If you don't have your calculator, they are very, very careful to give you a function where the numbers are manageable. And that can be done. It's just hard to do. So for me, I know you have your calculator in your hand, so I'm not too worried about the numbers being manageable by hand. But if they give you a no calculator question, obviously they don't expect you to do crazy calculations, right? The test is about whether or not you know Newton's method, not how good you are at chugging out divisions and additions of crazy decimals and fractions. So, okay, the best thing you can do for yourself is practice this to make sure that you have a system for organizing yourself and not getting lost in this. Again, this table is kind of my system. It works for me, but if you have a different way to write it that works for you, by all means use it, as long as you are making clear to whoever is reading it where you're getting your y values, where you're getting your slopes, and then where you're getting your approximations from. All right, so you can practice this in the Pearson assignment. You can ask me anything you want. But again, most of this is just practice and you finding what works for you as far as keeping yourself organized. All right, I'll see you in class. Have a good one.